Hello, this is Dr. Joe Trout from the physics program at Stockton University. And in this lecture, finish things up by talking about black holes, curved space-time, and galaxies. So if we look at the stellar mass black hole, on the left we see a visible light image that shows a region of the sky in the constellation of Cygnus. And the red box marks the position of an X-ray source. And this is Cygnus X1. And it's an example of a black hole created when a massive star collapsed at the end of its lifetime. So if you remember, what can happen is after the fuel burns out, the star begins to collapse. And Cygnus X1 is part of a binary star system. And the picture on the right shows an artist's rendition or illustration. And it shows the black hole here, and it's sucking off mass from its companion star. And what we see is that we get these powerful jets that are redirected out of the black hole, the area of the black hole. So this work began with Albert Einstein, and he's famous for his theories of relativity. So for example, if you go up in an elevator and the elevator is accelerating, meaning it's going faster and faster and faster, or it was going fast and going slower and slower, what you'll notice is that your weight will appear to change. So if the elevator is standing still, you have your weight. And if you're going down and you're accelerating, so you're going faster and faster and faster down, you'll feel lighter, right? And you can feel it on your legs. And if you were standing on a scale, you'd actually look lighter. It would read that your weight was lighter. If you were going up faster and faster and faster, you would actually look heavier than normal. And you can feel it in your legs, right? You could feel the force on your legs more than just your weight. And the scale would show your weight increasing. If the cable broke, God forbid, and the elevator car went into free fall, then you would appear weightless, right? Because the elevator car would actually be accelerating at the rate of gravity. And we talk about free fall. So whenever you, for instance, throw something and the only force acting on it is gravity, so for instance, there's not much air resistance and other things aren't happening, we call that free fall. So for instance, if you just drop a golf ball and it's not moving, it's never going to pick up speed very much, then we call that free fall. Or if you toss a ball to somebody across the room and you don't toss it at such a high speed that air resistance comes into play, that's what free fall is. So here's a weird thing. Let's say you jumped off of a cliff, and you and your friend jumped off at exactly the same time. If you wanted to toss a ball to them, you would toss it straight out because you'd both be falling at the same rate. And by the way, the ball would also be falling at the same rate. So to you, it looks like you're just throwing the ball straight out to your friend. But somebody observing it would see the ball have this curved trajectory. Okay, so if two people play catches, they descend in a bottomless abyss. Since the people in the ball fall at the same speed, it appears to them that they can play catch by throwing the ball in a straight line between them. However, when we look at it, we see the ball taking a curved path. So here shows some astronauts aboard the space shuttle, and they're shown in the Endeavour in 2008, and there's various fruit floating freely. And this is because the shuttle is in free fall as it orbits the Earth. So it's actually, as it's rotating the Earth, and the moon is the same way, it's actually in free fall. It's continuously falling towards the Earth. So this free fall, or this acceleration due to gravity, gives the objects and the people this weightless effect. So if we look at a curved light path, so if we see a spaceship and it's moving to the left as it orbits about a planet, if we take a light beam and shoot it towards the front of the ship, and meanwhile the ship is actually falling in a straight path, is only actually falling towards the Earth, and we might therefore expect the light to strike at B prime and above the target in the ship. Instead, the light follows the curved path and strikes at C. And in order for the principle of equivalence to be correct, gravity must be able to curve the path of light just as it curves the path of the spaceship. Okay, so what we're saying is, remember when we talked about being on the plane and you toss a pen to someone and the other person catches it, nothing weird happens? Well, that light has to follow that same rule. So this shows the space-time diagram, and this diagram shows the progress of a motorist traveling east across a flat Kansas landscape. And the distance traveled is plotted along the horizontal axis, and the time elapsed since the motor left the starting point is plotted along the vertical axis. So normally we see distance versus time. This is time versus distance. And what you can see is in the first about the first 60 seconds, you've traveled almost 150 miles, right? And if we look between 60 seconds and say 90 seconds, you're actually standing still. So your position didn't change. And finally, from about 90 to about 120, you traveled, about 60 miles. Or kilometers, excuse me. All of them are in kilometers. And the times are in minutes. Okay, so if we look at this analogy for space-time, we'll take a rubber sheet and we'll lay it across a table. And let's say that there's an ant crawling across the table, and it would just walk across in a straight path. If we stuck a rock in between, and so it pulls the sheet down, this is what space-time looks like. So for instance, now the ant has to travel across and down and back up, and this is what the ant's path would look like. So some of the evidence of this is Mercury's wobble. So the major axis of the orbit of a planet, such as Mercury, rotates in space slightly because of various perturbations. And in Mercury's case, the amount of the rotation or orbital precession is precisely explained by the general theory of relativity. And Mercury, being the planet closest to the Sun, is most affected by this warping of time-space. And the change from orbit to orbit has been significantly exaggerated in this diagram. It really isn't this big, but just to give you an idea of what it looks like. Some more evidence is this is the curvature of a light path near the Sun. So what we see here is that there's a star back here behind the Sun, right? And what we would see is that the sunlight would block any possibility of seeing the star. Right? So let's say we don't see it. However, we look in our telescopes from Earth and we actually see a star that's coming from back here. Well, really what happened was we're seeing starlight that's coming from the star, and it would get blocked by the sun, but what's going to happen is instead it gets bent and refracted in a way, and we can see it on Earth. So even though the star, we wouldn't be able to see it because the sun's in the way, we can still see it, and the reason is because the light bends around the sun. So this is more evidence of the theory of relativity. We also see that there's time delays for radio waves near the sun. So we had the Viking lander on Mars, and we're delayed when it passed near the sun and when space-time is curved relatively strongly. And in this picture, space-time is pictured as the two-dimensional rubber sheet. So what happens when we get a black hole? So at left, we see an imaginary astronaut floats near the center of a massive star core about to collapse. And as the same mass falls into the smaller sphere, the gravity at its surface increases, making it harder for anything to escape the stellar surface. And eventually, the mass collapses so it's so small, in fact, we believe that it actually that the mass actually compresses to a point, and that the escape velocity is so high that even light can't get out. You also notice that the astronaut is getting stretched as the star collapses. This is John Wheeler, and is a physicist who did much of the pioneering work on general relativity and popularized the term black hole, this hole which even light can't get out of. So here shows a star, and if we shine a flashlight up at the star, what would happen is we get these light paths that come up. So if I threw a ball straight up, it would come straight back down. If I threw a ball off at this direction, it would curve around and come back to the planet. Right? But light's moving really fast, so we don't notice the curvature on this massive star. But when the star collapses, gravity increases, and what we'll see is that any of these rays that we're pointing out at some area would feel the pull of gravity and get pulled down in a parabola, somewhat like a ball would. This is Carl Schwarzschild, and he's a German scientist, and he was the first to demonstrate mathematically that a black hole is possible, and he determined the size of a non-rotating black hole event horizon. So this event horizon is the horizon where you can't see anything that's going on inside the black hole, because anything in that event horizon won't get out. So here we see a binary black hole. Once again, this is an artist's rendition, and it shows a black hole and a star, and the star is red, so it's a red, probably a red giant. And as matter streams from the star, it forms a disk around the black hole, and something of the swirling material close to the black hole is pushed outward perpendicular to the disk in these two narrow jets that we see here. So don't forget, no light gets in here, and but what we're seeing is that this black hole is receiving material from the star. This is a gravitational wave telescope. So what we're looking at is gravitational waves as they travel through the atmosphere. And its upper left and far right, the image, are 4 kilometers long detectors. Right, so if you remember, 5 kilometers is about 3.1 miles, right? 3.12 miles. So this is probably close to around 4 miles. I'm sorry, close to about 2.5 miles. So here's the signal that was received by the gravitational waves. And what we see in this top panel and the middle panel are the signals that were measured. And the smoother thin line curve in each of the panels is the predicted symbol or signal from Einstein's theory of relativity. And the painting shows an artist's impression of 2 massive black holes spiraling inward towards an event merger, right? So that they're spiraling in towards one another. Okay, so now we live in the Milky Way galaxy, right? And the Milky Way rises over a square tower, an ancestral Pueblo building in this national monument in Utah. And many of the stars and dark clouds of dust combine to make a spectacular celestial sight of our home galaxy. And this location has been designated an International Dark Sky Park by the International Dark Sky Association. So William Herschel was a German musician who immigrated to England and took up astronomy. And he discovered the planet Uranus and built several large telescopes and made measurements of the sun's place in the galaxy and the sun's motion through space and the comparative brightness of stars. So he did a lot of work, and this was just his part-time job, right? This was just something he did as a hobby, really. And Herschel's diagram of the Milky Way, and it was constructed, and he constructed this cross-section of the galaxy by counting stars in various directions, and he shows the location of the sun. So this diagram shows the location of globule clusters with the position of the sun also marked. And the black area shows Herschel's old diagram, and it was centered on the sun, and it's approximately to scale. So if we look at a schematic representing of our galaxy, what we see is that the left image shows a face-on view of the spiral disk. So our it shows this spiral disk and these lines coming off of it. And there's kind of a bulge in the center. So this is looking straight down on it. If we turn it sideways, right, if we view it from this area, what we would see is something that looks like this, right? So a bulge with a whole bunch of stars in the center, and then these straight lines coming down. And once again, if we flipped it so that we could look at it straight on this way, this is what we would be seeing. And here's these spiral arms that are coming out, and the location. Oh, also, we show where the position of the sun is, right? And where we would see the sun. So these spiral galaxies come in 2 flavors, right? Unbarred and barred. And the first image shows an unbarred galaxy, and what we see is a bulge in the center, and you can see these arms that are spinning out, spiraling out from there. This shows a strongly barred galaxy. So what there is like a thick line of stars in here, and then the spiral arms come off of the bar. Here shows the inner part of the Milky Way, and this is an infrared map showing 500 million stars. And it was obtained as part of a 2-micron all sky survey, so 2MASS, and because of the interstellar dust does not absorb the infrared as strongly as visible light, this view reveals the previously hidden bulge of old stars that surrounds the center of the galaxy, along with the galaxy's thin disk component. So the major parts of the Milky Way galaxy in this are shown in this schematic. And what we see is that there's a bulge here. The sun's actually over here. And here's the center of the galaxy. Then there's a thin disks with lots of stars. And then there's a thicker disk with some stars. And then there's this halo that contains some other stars. So there's a couple myths of the Milky Way, and you can read up on them if you'd like. Right? So the Milky Way bar and its arms, here we see the Milky Way galaxy as it would look from above. And this image is assembled from data from NASA's WISE mission. So you can see that there's two spiral arms that come out that have lots of stars, and there's two other spiral arms that have fewer stars. So the Orion Spur, the sun is located in the Orion Spur, which is the minor spiral arm located between those two other arms. And in this diagram, the white lines point out some noteworthy objects, which you can take a look at. So how did the arms form? Well, we believe that the arms might have come from irregular clouds of interstellar material that were stretched out by different rotation rates through the galaxy. Right, so these regions, here's these two interstellar guards, and they start to rotate, and part of it is moving faster than other parts, and what we can see is that these will start to like wind up and form these spiral galaxies. So if you look at the rotation of the curve of the galaxy, we have the orbital speed of carbon monoxide and hydrogen gas at different distances from the center of the Milky Way galaxy, which is shown in red. So if we look at the radio image of the galactical center region, right, this is a radio map of the center of the galaxy, and it was constructed from one of the very large array radio telescopes. And this is an artificial color mosaic of 30 images, right, taken with the Chandra X-ray satellite, and it shows a region of about 400 to 900 light years in extent, and it's centered on Sagittarius A, and the bright white source in the center of the picture, and the X-rays emitting point sources are white dwarfs and neutron stars and stellar black holes, right? And the diffuse haze is emission from gas at temperature of 10 million Kelvin. And this hot gas is flowing away from the center out into the rest of the galaxy. And the colors indicate the X-ray energy bands, right? So red is low energy, green is medium energy, and blue is high energy. So here's another image that was taken with the very large array of radio telescopes, and it shows the radio emissions from a hot ionized gas at the center of the Milky Way. And the lines slanting across the top of the image are these gas streams. And they're much easier to see with the radio telescope. If we look at near-infrared images, so this in essence is heat, right? So near-infrared. So the image shows the center of the galaxy, and it's observed by the giant Keck telescope. And it tracks the orbiting stars measured from 1995 to 2014. And they've been added to this snapshot. And the stars are moving around the center very fast, and their tracks are consistent with the single massive gravitator, right, that resides in the center of the image. So this shows Andrea Ghez and her team has helped shape our understanding of supermassive black holes. So objects orbit, how objects orbit the galaxy. And so in this image, we see stars and a thin disk of our galaxy in a nearly circular orbit. And in this image, you see that the motion of the stars in the galaxy halo, and they're randomly oriented. So we have a bunch of stars that are rotating, orbiting in this direction, and then we have halo stars that are orbiting like here. Heroes? Sorry for that pause. The Andromeda galaxy is a neighboring spiral um, galaxy, and it looks similar to our own galaxy in that it's a disk galaxy with a giant bulge. And note that the bulge of older yellow stars in the center and the bluer younger stars are in the outer region. So when we look at how the galaxies form, right, we could see according to this model, the galaxies were initially formed by a rotating cloud of dust that collapsed due to its own gravity. And the halo stars and globule clusters either formed prior to the collapse or they were formed elsewhere. And the stars, and then captured by the galaxy. And the stars in this disk formed later when the gas from which they were made was already contaminated with heavy elements produced by earlier generation of stars. And here we see a picture of the Sagittarius dwarf, and the British astronomers discovered a galaxy in the constellation Sagittarius, which is located only about 50,000 light years from the center of the Milky Way galaxy, and is falling into our galaxy. So we see the streams of the galactic halo. So when a small galaxy is swallowed up by the Milky Way, its member stars are stripped away and form streams of stars and galactic halo. And this image is based on the calculations. I only have a couple more minutes. You can turn it up. Okay. I know I'm doing this because it's a good thing. So here we see the globular cluster M54, and this is a Hubble telescope image, and shows the globular clusters, which is now believed to be the nucleus of the Sagittarius dwarf galaxy. And this has been a really long process, right? So we're talking about 3 to 4 billion years, and here shows some images of what it would look like. Okay, so here we see a spiral galaxy. So this is NGC 6946, and it's also known as the fireworks galaxy. And it's a distance of about 18 million light years in the direction of the constellation of Cephus and Cygnus. And it was discovered by Herschel in about 1798. That's about one-third the size of the Milky Way. Here we see the Andromeda galaxy, and it's also known as catalog number M31. And this galaxy is a large spiral galaxy, very similar in appearance to and slightly larger than our own galaxy. So at a distance of about 2.5 million light years, Andromeda is a spiral galaxy that is nearest to our own galaxy. Also, you can see in the distance there's two of its satellite galaxies. So Edwin Hubble um, established some of the most important ideas according to the study of galaxies. So first we have these spiral galaxies, and this is the spiral arms of M100, and are bluer than the rest of the galaxy, indicating that the young high mass stars and star forming regions, right? And we view the spiral galaxy um, NGC 4565 almost exactly edge on. So from this angle we can see that the dust in the plane of the galaxy, and it appears dark because it absorbs um, light from the stars in the galaxy. So here's an example of a barred spiral galaxy, and this is NGC 1300, and it's a spiral barred galaxy. And note that its spiral arms begin and end at each bar. So here's the bar, and the spiral galaxies come off of either side of the bar. So Hubble felt that um, the classification looks something like this. We have these elliptical, well, circular and then elliptical galaxies, and then they go off on branches on either side. And what we can tell is what the age of these galaxies are. So they would either go off as a spiral galaxy or a bar spiral galaxy. And as time increases, we'll see what they would look like. So the elliptical galaxy, this is ESO 325-G004, is a giant elliptical galaxies. And other elliptical galaxies can be seen around the edge of this image. And if we look at B, right, this is an elliptical galaxy, probably originated from the collision of two spiral galaxies. So here we see a dwarf elliptical galaxy, M32, and the dwarf elliptical galaxy and one of its companions to the giant Andromeda galaxy. And here we show the 4-meter telescope, and the Milky Way is seen to the right of the dome, and its large and small Magellanic clouds are seen to the left. M101 is a pinwheel galaxy, so this is a spiral galaxy, and this galaxy is face-on spiral at a distance of about 21 million light years. It's almost twice the diameter of the Milky Way, and it contains at least 1 trillion stars. Here we see a Cepheid variable star, and in 1994, using the Hubble telescope, astronomers were able to make out these individual Cepheid variable stars in the galaxy M100 and measure its distance and to be about 56 million light years. And the insets show that the star at 3 different nights, and you can see the brightness of this, that the brightness changes as on these 3 bright nights, or the luminosity changes. So if we look at a type 1a supernova, The bright object at the bottom left center is a Type 1a supernova, and it's near peak intensity. And the supernova easily outshines its host galaxy, and this extreme increase in luminosity help astronomers use the 1a supernova as standard bulbs to see what's to compare other things to. So here we see Vesto Cipher, and Cipher spent his entire career at the Lowell Observatory, where he discovered large radial velocities of the galaxies. And we look at Hamilton was Hubble's collaborator in the great task of observing and measuring the characteristics of many of the galaxies. So if we look at Hubble's law, we see that this data shows Hubble's original velocity distance relationship adapted to his 1929 paper that he wrote. And what we see is that this is the velocity of the galaxies, and this is the distance in millions of light years, right? And here's Hubble's, and so this was done a second time by Hubble and Hamilton, and who added their data. So you can think of this as kind of stretching a ruler. So as ants are on a ruler, and it sees other ants moving away from them, right? So the speed at which another ant moves is proportional to its distance. So if we look at how the universe is expanding, we think of raisin bread. So if you've ever made bread, you can put yeast in and then let the yeast rise and the bread becomes bigger. So we can think of this expanding universe as looking at these expanding raisin bread where the raisins are the stars. So as the raisin bread rises, the raisins see other raisins moving away. And the more distant raisins move faster in the uniform expanding bread, right? So it looks like they're moving faster. All right, so that ends our discussion on um, galaxies, and thank you for our time.